Thanks. Can you hear me? Okay. Yeah, it's my great honor to be here as a recipient of the award, and I will present a work titled "Assumption Linear Analysis of Cluster Randomized Trials in Infectious Diseases for Intent to Treat Effects and Network Effects." So this is one of the work during my PhD life, which is jointly done with my PhD advisor, Dr. Hyun-Sung Kang, who is the assistant professor at the University of Wisconsin-Madison. So as written in the title, I'm going to discuss the cluster randomized trials, which is a specific experiment where treatment is randomly assigned at cluster level. So I'm going to give you two examples. The first example, the first experiment was conducted by Coying et al., which I will call as Hong Kong study. And in this experiment, face mask recommendation is assigned to each household. And the second example is the experiment done by Defle et al. And in this experiment, a new HIV education program is assigned to each school. And unfortunately, in many CRTs of infectious diseases, such as Hong Kong study, both interference and non-compliance are present. So what is interference? So interference is a specific phenomenon in causal inference where peers treatment usage can affect eagle's outcome. So as you can see in this diagram, the interference pattern can be very complex. However, in many cases, there are some special cases where interference pattern can be simplified. So we call this phenomenon as partial interference, where interference only happens within non-overlapping clusters, as you can see in this graphical illustration. So interference only occurs within non-overlapping blue bubbles. And what is non-compliance? So non-compliance is another phenomenon where one's actual treatment usage is different from the randomized treatment assignment. So Engels, Invens, and Rubin considered 4 principal strata based on the treatment usage under control and under treatment. So if individual is assigned to control, he or she can decide whether to use treatment or not. And similar thing happens when he or she is assigned to treatment. As a result, there are 4 possible cases. The first group of individual is known as always takers, who always use treatment regardless of the assigned treatment. And the second group of people is known as compliers, who comply to the given treatment status. And the third group of people is basically kindergarten students who behave exactly the opposite to the assigned treatment. However, we usually assume that there is no defier in the population. And the last group of people is never takers, who never uses treatment regardless of the assigned treatment. And I'm going to describe why the interference and non-compliance issue occurs as in the Hong Kong study. So in the Hong Kong study, 96 households with 1 infected individual were recruited, and 45 households were randomly assigned to receive face masks and hand sanitizer, which I will call as treatment in today's talk. And the goal of the study is to study the effect of using face masks and hand sanitizer on the secondary attack rate of influenza in the household. In this data set, we find non-compliance issue is present because roughly 45 individuals in treated household did not use face masks, indicating that these individuals are never takers. And also 2 individuals in control household used face masks, indicating that these individuals are always takers. And also interference is likely because father mother's face mask usage can affect children's influenza infection. And also the past works show that household is a key unit of influenza transmission due to the closeness between household members. Moreover, the Hong Kong study was limited to a household that already included the flu-infected individual, which shows the interference, the magnitude of the interference among household members is much larger than the degree or the magnitude of the interference across individuals in different households. So as a result, we believe the partial interference is a plausible approximation that describes the Hong Kong data set. So the main goal of today's talk is to focus on 3 target estimates that occurs in CRTs with interference and non-compliance. The first effect is the effect among never takers. That is, we are curious whether individuals not using face masks can get extra protection from their peers' mask usage. And similarly, we want to find the effect among always takers. That is, we are curious whether the individuals always using face masks can get extra protection from their peers. And the last effect is the effect among compliers. So what are the effects among individuals who comply to the assigned treatment? And if you're familiar with the causal inference, then the first goal is to find, the first question is to find whether these effects are point identifiable from the observed data. And we are trying to answer the following question. However, it turns out that these effects are not point identified in general. So that is, we need to make additional assumptions to point identify these three effects. However, these effects are not plausible in many CRTs, including Hong Kong study. And we take a step back and set a more realistic goal. That is, can we partially identify these three effects by constructing bounds? And the answer is yes. So we develop a new methodology that has two steps. In the first step, we construct this compliance type classifiers using regression or machine learning models. And in the second step, we use classifier-based quantities to bound these three network effects using via linear programming. And we study how to estimate the bound and study its statistical properties. So this is the most painful slide. I'm going to rush through the notations very briefly. So I use double subscript JI to denote individual I in cluster J, such as Bob, Sally, or Chen. And I use XJI to denote the pre-treatment covariate of individual, such as age, gender, household size, or vaccination history. And ZJ is a binary variable which shows the cluster level treatment encouragement, where Z equals to 1 means the household is encouraged to use face masks. And D parenthesis small z, which is also binary, is a potential treatment receipt under given treatment status. And D equals to 1 means individual uses face masks under given treatment status. And Y angle Z, which is bounded in the unit interval, is the potential outcome under given treatment status. And Y angle Z means that individual is healthy under given treatment status. So I want to expand the notation of Y angle Z. So this is the potential outcome under given treatment status, which is written in red. And also the Eagles treatment usage is set to be the natural treatment receipt under given treatment status. And Pierce treatment usage is also set to be the natural treatment receipt of the Pierce. And if you are familiar with the instrumental variable settings, then under the exclusion restriction, then there is no effect of encouragement on the outcome once the actual usage is fixed. That is, this Y angle Z is the individual JI's outcome if household members use face masks based on their compliance type under given treatment status. And in this setting, we consider finite population framework where the encouragement is the only random variable. That is, pre-treatment covariate and the potential treatment receipt and the potential outcome. All of these values are considered to be a fixed number. And as a result, the observed treatment receipt, DJI, is the random only in the sense that it is a realization of either D1 or D0 based on the random assignment. And the same story carries over to the observed outcome. And as I mentioned, we are going to focus on three network effects, the effect among never takers, awake takers, and compliers. So I'm going to illustrate by only using the effect among never takers. So which is the average of the difference between two potential outcomes only among never takers. So visually illustrate this. Let us consider a household having 5 members. And if this household is assigned to treatment, then you may see the following result, where 4 individuals use face masks, whereas the one in the middle does not use face masks. However, if this treatment is assigned to control, then you may see a different result. Under this case, now 3 individuals do not use face masks, whereas 2 individuals still use face masks. So by seeing this plot simultaneously, we find 2 individuals in the bottom are always takers, and 2 individuals on the top are compliers because they behave exactly the same as the given treatment status. And one in the middle is a never taker because he or she never uses treatment. And basically, we are going to compare the potential outcome of the never taker under treatment and under control. If these 2 outcomes are the same, it means peers using face masks do not benefit this NT. And as a result, there is no effect among never takers. On the contrary, if the outcome under treatment is better than that under control, it means peers using face masks do benefit this NT. And as a result, there's a positive effect among never takers. We can similarly define the effect among never always takers and compliers. However, as I mentioned, these effects are not point identifiable unless we make strong assumptions and or particular experimental designs are used. So I'm going to give you the rough idea why these assumptions are not plausible to analyze the Hong Kong study. So Zhou and Stewart proposed to assume either one of the following two assumptions. The first assumption is principal ignorability, where compliance type is conditionally independent of the outcome, potential outcomes, given observed characteristics. So as you can see in this graph, once we conditioning on the observed characteristics, now the compliance type and the outcome are conditionally independent. That is, the potential outcomes are the same, or the distribution of the potential outcomes are the same across three compliance type once we fix on the observed characteristics. However, in the Hong Kong study, unobserved characteristics such as health-seeking behavior may exist. So suppose that I have a twin brother who has exactly the same characteristic as mine. Then if I'm a health-seeking person, then I will wash my hands more frequently. Whereas my brother is dirty, then he may not want to wash his hand. Then the probability of me being always taker is higher, and also as a result, the health status of mine would be better than my brother's. So it means that despite we have the same characteristics, the compliance status and outcome may not be conditionally independent. So this assumption is not plausible. And also they considered exclusion restriction plus no interference, meaning that the potential outcome only depends on ego's actual treatment usage. That is, if I'm a never taker, then I will never use treatment, which means my treatment receipt is always fixed to 0, which makes the difference between two potential outcomes be 0. As a result, there's no effect among never takers, and there's no effect among always takers too. However, we are thinking that there could be a possibility of interference, which means the potential outcome of ego not only depends on ego's treatment usage, but also depends on peers' treatment usage as well. So this assumption is not plausible as well. So what can we do? We consider assumption lean approach in the sense that we make only standard assumptions in CRTs and obtain sharp bound of network effects using machine learning and linear programming. So these are these assumptions for Hong Kong study, which can be understood as the extension of previously mentioned Engris et al.'s paper to the Hong Kong study setting. So the first assumption is partial interference, and the second assumption is cluster random assignment, which are plausible to describe this Hong Kong data. And the third assumption is there is at least one complier in the population. And the fourth assumption is there is no defier in the population, which are also plausible in many CRTs. And the fifth one is the network version of exclusion restriction. That is, the intervention, the recommendation only affects the ego's treatment, one's outcome only through the actual usage of the household members. The last assumption is not standard, but plausible to describe Hong Kong data. It means that the outcome is bounded and monotonic. And in the setting, the outcome is binary. It is an indicator whether the individual is healthy or not. So it is already bounded in the unit interval. And also the intervention, which is the recommendation of using face masks, is not harmful, seemingly not harmful for one's fluid status. So in that sense, the outcome is monotonic in terms of the recommendation. Actually, we can drop this assumption, this monotonic portion, but it will give the wider bound at the end of the day. So it helps to tighten bound by using the subject matter knowledge. In the first step, we construct classifiers, and which can be potentially imperfect for each compliance type using the regression or machine learning models. And in the second step, we use classifiers from the previous step and use the above assumptions to construct bounds for the network effects via linear programming. So let me go through the first step. So this plot illustrates the distribution of the never taker across one age variable. And as you can see, if the age is younger, then he or she tends to be never taker. In the first step, we consider a transformation of the age variable from a risk minimization. So you can simply think it as regress the never taker indicator on age variable based on the penalized logistic regression model or just a linear regression model. And once you obtain this curve, which is drawn this gray curve here, and in the second step, we consider to obtain a threshold Q star, which is drawn by this dashed line. It makes the number of classifier based and true never taker equal. That is, the number of dots in this blue area is exactly the same as the total number of never taker in the population, which is 9. And in the third step, we actually classify those 9 individuals as never takers and count the number of misclassified never takers, which is 2. And in the procedure, we can see that the number of misclassified never taker is strictly positive, indicating that the classifier doesn't have to be perfect. And actually, then, for example, suppose the generating model for the never taker status is quadratic. However, to construct the classifiers, it is allowed to use misclassified models, such as the linear regression model or just the intercept model. That is, our method is robust to the model specification, model misspecification. At what expense do we get this robustness? If you use better classifiers or more accurate classifiers, then you will have a tighter bound at the end of the day. However, it doesn't mean that we must use the correct classifier, but actually you can use the wrong classifier, and our method is valid. However, you will get the wider bound at the end of the day. We can similarly construct always takers and compliance classifiers too. So in the second step, we use the compliance type classifiers and standard assumptions to construct linear constraint script C. So for example, it turns out that we need to bound the following two quantities, which are the potential outcome under control only among misclassified never takers, and the potential outcome under treatment only among misclassified never takers. So by using the bounded outcome portion, we can find the lower bound and the upper bound of these two quantities, which are 0, and the total number of misclassified never takers in the population. And using the monotonic portion, we can give the relationship between the inner two quantities. And once we construct these linear constraints, we can solve the linear program to minimize and maximize the network effects subject to these linear constraints. And we will call the solution as the lower bound and the upper bound of the network effect. And our methodology is similar to Bulk and Pohl's LP bound in instrumental variable settings. However, our methodology focuses on subgroup network effects, whereas their methodology focuses on average treatment effect. And our methodology also uses covariate adjustment to further sharpen bounds. And there's one requirement for constraints. The outer quantities, which are written in blue, should be identifiable from the observed data. And this is necessary for the consistent estimation of the bound. Do we need the correct classifiers for the identifiability? As you can imagine, the answer is not necessarily. So suppose the true model is quadratic. However, if we decide to use the intercept model, then the best misspecified model is to choose the intercept as the proportion of never takers in the population. And there is a consistent estimator of the proportion of never takers. And as the number of cluster increases to infinity, we can show that this estimated proportion converges to the true proportion of the never takers in probability under mild conditions, which means even though we use misspecified classifiers, still there is a way to identify the quantities. And I'm going to summarize the key properties of this methodology. The first property is that our methodology is invariant to affine transformations of the outcome. That is, if we construct the bound using the transformed outcome, here the transformed outcome is the original outcome multiplied by the scale factor B and shifted by a parameter A. Still, the bound is reasonable in the sense that the bound from the transformed outcome is the same as the original outcome multiplied by the positive scale parameter. And the second property is that regardless of the quality of classifiers, our bound is valid in the sense that it will always cover the true network effect. And the third property is that given classifiers, our bound is sharp. That is, unless you change the classifier to better one, this is the best possible solution. That is, it is the narrowest possible given these particular classifiers. However, if you use a better classifier, that is, if the classifier has a lower misclassification rate, then our bound is getting narrower and narrower. And in the extreme end, if the classifier has zero misclassification rate, which means if the classifier is perfect, then our bound shrinks to the point which is the true network effect. In that case, you can point identify the effect. And in the fifth property is that under some mild conditions on classifiers, such as, for example, if you use the loss function if you use the smooth loss function, then this bound can be consistently estimated. And for inference to construct the uncertainty interval, we use resampling approaches such as bootstrap or subsampling that are modified for cluster level resampling. So I'm going to describe the fifth property very briefly. So what I have discussed is following. So we have a population which we cannot entirely observe. Still assume that you have that data. And we, using all clusters, we define the true or the posited specified never taker classifier. And using the population level classifier, we obtain the population level constraint script C, which uses the proportion of misclassified never taker as 2/9. And using that population level constraint, we solve the linear program to find the lower and upper bound, which lower and upper bound as lower and upper bound. However, actually, we cannot identify all of the compliance type. Actually, there are only two groups of people where we can whose compliance type can be identified. The first group of units are the units who are treated, but who did not use treatment, which are never takers. And in the second group is the units who are in control household but used treatment. Then these individuals are always takers. So by only using the treated clusters where we can identify the never taker status, we can estimate the never taker classifier. So as you can see, the population level classifier curve and the classifier curve from the treated cluster looks slightly different. And by using the estimated classifiers, we can obtain the estimated constraints, which uses the estimated proportion of misclassified never taker as a quarter, which is different from the true proportion of misclassified never takers, which is 2/9. And by using the estimated constraints, we can actually solve the linear program again, and that becomes the lower and upper bound estimate. And under some regularity conditions on classifiers, and plus using the fact that this is a randomized experiment, we can show that the estimated constraints converge to the true or the population level constraints in probability. And we find that the solution to a linear program is a continuous function in its constraint. As a result, we can use a continuous mapping theorem to show the consistency of the bound estimate. We simulate our findings based on the Hong Kong study design. We use the same subset of covariate and cluster structure and randomization probability. So we generate the compliance status based on the gender and age variable. So in a nutshell, female shows the more sharper decision boundary compared to male, and individual is more likely to be a complier if their age belongs to this blue range, and more likely to be an always taker if their age belongs to this red range. Otherwise, he or she is more likely to be a never taker. And we generate the potential outcome from a Bernoulli distribution, where the probability has a logistic form of vaccination history and compliance type. Once we generate the data, we find the effect among always taker is the smallest and the effect among complier is the largest, but these effects are not point identifiable. So as a result, we try to construct population level bounds by using our approach with linear regression and penalized logistic regression. There is an existing method that does not use classifier. However, there is one limitation. This methodology cannot use continuous variable. That is, they can only use discrete variable. That is, age variable cannot be used without discretization. So once we generate the population level, once we calculate the population level bounds, so here's the result. All bounds include the true estimate. For example, the effect among never takers, which is 0.15, always belong to these intervals. And same story goes to effect among always takers and compliers. when we compare the length of the interval, we find machine learning bound, our methodology using penalized logistic regression leads to the narrowest bounds. The reason is our bound can use age variable, which is a key to explain compliance type, whereas the non-machine learning bound cannot directly use it unless they discretize it. And we can further sharpen bounds by combining our methodology and non-machine learning bound by taking intersection. So now we move to the estimation portion. We randomly assign treatment 1,000 times for this simulated data with 95% bootstrap confidence interval. And here's the result. Each row shows each estimate, and each column shows each methodology. Here, blue dashed line shows the true network effect, which cannot be point identified. And red solid lines are the lower and upper population level lower and upper bound, which can be consistently estimated. And this red histogram and blue histograms are centered around the lower and upper bound, population level lower and upper bound, which shows the consistency of the estimate across all methodology. And when we see the coverage, empirical coverage of the 95% bootstrap confidence interval, it is always greater than the nominal coverage, which supports the which validates the usage of the bootstrap-based confidence interval. We apply our method to our motivation example, the Hong Kong study. We use 13 pre-treatment covariates such as age, gender, household size, and vaccination history. We only report the estimation result of the never taker effect and complier effect because the bound of always taker effect are reduced to 0. And here is the result. Let me go by one. So the classifier-based bound of the never taker effect and complier effect are 13% and 20% narrower, respectively, compared to the non-machine learning bounds. However, when we see the lower bound estimate, our things are worse in the sense that our things hits 0, whereas the non-machine learning bounds is strictly positive. However, there's a way to improve these bounds by taking intersection. So this is the best possible solution, which shows that effect among never takers is positive, which means there could be a spillover effect among peers to never takers, which suggests a way to protect mask refusers. However, there's a lack of statistical evidence at 5% level. So let me briefly summarize what I have discussed. In CRTs with interference and non-compliance, network effects may exist but are not point identified. So we consider a methodology to obtain sharp bounds of network effects using regression machine learning models plus linear programming. And the classifiers don't have to be perfect, but more accurate classifiers lead to shorter bounds. Even classifiers, our bounds are the sharpest possible. And under mild conditions, this bound can be consistently estimated. And the presented bounding approach may be applicable to other instrumental variable settings. Thank you for having me. And again, it is my great honor to be here as a recipient of the award. And thank you for my PhD advisor, Dr. Hansen Chang. Thank you.
Thanks a lot for the great talk. Any questions from the audience?
Hopefully you can hear me.
Yes.
As you can always see intersection from different methods, does it sort of synthesize which five many things possible?
Oh, excuse me?
Because you always see intersection from different methods, right?
Yeah.
So does that kind of incentivize you to take which try as many methods as possible, essentially? It's always not.
Yes, that's true. But I think the problem is how to construct this confidence interval as well. And not only that, there are very few literature that can address interference plus non-compliance. So there are many ways to address either one of those. Like if you are only tackling interference or non-compliance, there are several methodologies. But based on my knowledge, there are very few approaches that can address both when both issues happen. Yeah, but that's a great question. Does that, yeah.
Add as many as you can.
Yeah, if it exists, then you can improve, but still, yeah, I think the problem is actually constructing this confidence interval, which still remains as a future direction in my even for my project as well.
I mean, in a way that's good because method will get better with time.
Yes.
It will be better more.
Yeah. To add to your question, there are several ways to actually consider different methodologies, such as you can use the tree or the random forest based models. In that case, even by improving our classifiers, then you can still further sharpen bounds probably. Yeah. Thank you.
Any other questions? Right. Great. Okay,
Thank
let's
you.
thank the challenge again.